Even though Arrhenius theory advanced our understanding of acids and bases significantly, it still had certain problems associated. For example, Arrhenius theory had a really hard time explaining why is ammonia a base. Even though ammonia reacts with acids just like sodium hydroxide, it has no OH group associated. So according to Arrhenius theory, it should not behave as a base. So clearly there was something missing there, and that gap was filled by the Brønsted-Lowry theory, which was established in 1923. These two chemists got the Nobel Prize for their theory. In Brønsted-Lowry theory, acid is still defined as a proton donor. However, base is no longer defined through OH minus group, but rather as a proton acceptor. And so the key process in Brønsted-Lowry theory is the transfer of protons. For example, if we have HCl reacting with sodium hydroxide, then this will be donor, and this will be acceptor, and they would give a salt, sodium plus Cl minus, plus H2O. This theory would also apply to a reaction between HCl as a donor and ammonia as an acceptor, because ammonia would use its free electron pair to get to NH4 plus Cl minus. Okay? Even organic reactions such as reaction of HCl and ethylene could be explained this way, even though this is significantly shifted to the left. The reaction that occurs still protonates ethylene and gives Cl minus here. Now, Brønsted-Lowry theory can explain all of these reactions, and that was a good thing about this. One thing that was sort of inherently implicit in the Brønsted-Lowry theory is that upon protonation, a base becomes an acid, and an acid becomes a base upon deprotonation. So if you look at this equation, what we get here is HSO4 minus plus H3O plus. Clearly, in the forward reaction, this is an acid, and this is a base. But if we look at the backward direction of the same reaction, then H3O plus will donate back proton to HSO4 minus. So this is now an acid, and this is a base. And they're called conjugated acids and bases of the corresponding pairs on the left-hand side of the equation. The same would apply to the reaction of HCl and ammonia, which gives NH4 plus and Cl minus. This is an acid, this is a base, acid, and a base. Okay. The general relationship HA, so that's any given acid, would react with water to give A minus and H3O plus. In this equilibrium, what's characterized by equilibrium constant, which in this case is called the acidity constant Ka, and that is basically H3O plus on top times A minus over HA. We're omitting water from this equation because water concentration is constant. Since everything is dissolved in water, concentration is so large that it effectively does not change during the reaction. And this Ka constant is a measure of acidity, and it's sort of a characteristic of any given acid. And people often use pKa, which is defined in an analogous way to pH as a minus log Ka. Logarithmic scale is used because Ka values go anywhere between 10 to the minus 50 and 10 to the 10th. So they vary by 60 orders of magnitude. This is very difficult to deal with in linear terms, but in logarithmic terms it's simplified. The implicit assumption of Brønsted-Lowry theory is this interchange of acids and into bases as they lose their proton. And clearly, if a strong acid will very much want to give up its proton, but that also means that its conjugate base will not want that proton back, which means that the stronger your acid HA is, the weaker the corresponding conjugate base A minus is. And this is a general relationship. Now the reactions, acid-base reactions, always go from strong acid and strong base towards weak acid and weak base. And this again is a general relationship. If we wanted to quantify the basicity of conjugate bases, we can do that as well. So for example, A minus can react with H2O plus, and now water adds acts as an acid, so we get HA plus HO minus. A certain basicity constant Kb is now defined as HO minus times HA over A minus. Again, we are omitting the concentration of water. And the corresponding pKb value is defined as minus log Kb. Okay? It's interesting to see what is the relationship between acidity of an acid and basicity of its conjugate base. And to look at that, we can multiply Ka and Kb and see what comes out of that. And if you look at Ka, then it's H3O plus times A minus over HA, and all that times HO minus times HA and over A minus. A minus and A minus cancel out, and so do HA and HA, and what we're left with is H3O plus times HO minus, and this is nothing else but the ionic product of water, 10 to the minus 14th, which basically means that Ka equals 10 to the minus 14th over Kb. So it's inversely proportional to each other. Now, since we're here already, we might look at some characteristic numbers, see what's a strong acid, what's a weak acid. For example, HCl, which we know is a strong acid, has a pKa value of minus 2.2. Remember, with pKa, the lower the value, the stronger the acid. Acetic acid is 4.74. This means that it's about 10 to the 7 times weaker than HCl. Water is 15.7, and there are very weak acids like methane, which is more than 40. So methane is 10 to the 40 times weaker acid than HCl. This is a really powerful example of how widely do these numbers vary. Now that we've seen a little bit of this quantitative background to acidity and basicity, let's look at what determines the acidity of a given acid. And there are 3 factors that play a role. The first one is electronegativity. CH3 minus is unstable because, in part, carbon is not an electronegative element, and so it doesn't like having negative charge on it. But F minus is stable, since fluorine likes negative charge on it. What this means is that in the reaction CH plus water to give CH3 minus plus H3O plus, this reaction is unlikely because CH3 minus is unstable, so it's more likely that this will be shifted to this direction. In the same reaction with HF plus H2O, we get F minus, which is perfectly happy, and H3O plus. So this reaction is completely likely, and it will certainly be shifted towards the right. And that's why HF is strong acid. It's stronger than H2O, which is stronger than NH3, which is stronger than CH4. Okay? The second factor that determines acidity is the size of the anion. What does this mean? Well, negative charge is happier when it's spread out over a large surface. Remember from when we talked about resonance that delocalization of charge is always favorable. And if we can delocalize over several atoms, but also if we have a large atom, then just spreading it around that atom is already pretty localized. And that's why anion such as I- is more stable than Br-, is more stable than Cl-, which is more stable than fluorine-. So this is the order of stability of anions. What that means now is that once a corresponding acid gives up a proton to make one of these anions, if an anion is stable, it will not want to go back, which means that the corresponding acid is stronger. So Hi is stronger than HBr, which is stronger than HCl, which is stronger than HF, which is already an acid as is seen up here. So this is order of acidity. Finally, the last factor, and the one that we spoke about very recently, is resonance. Because resonance can stabilize anions by delocalizing their negative charge. So if we compare a series of anions, such as CH3O-, where this negative charge can only stay on this oxygen, versus our acquaintance of acetate anion, which can delocalize its negative charge over 2 oxygens, versus this sulfonate, which can delocalize its negative charge over whole 3 oxygens. This way. This anion is going to be the most stable because its negative charge is most extensively delocalized. And this should already tell you that the corresponding acid will be the most acidic one, since it gives an anion which is perfectly happy without a proton. So it doesn't want to take the proton back. And that means that the corresponding acid, which is methane sulfonic acid, is a stronger acid than acetic acid. It's a stronger, which is a stronger acid than methanol. And if you look at the pKa values, the number is illustrated. I don't have an exact number for this acid, but it's relatively strong acid. Its pKa is probably somewhere around 1. This is 4.7, and this is somewhere close to 16. So these values really vary dramatically.